All right, welcome back everyone. We've started in our last lecture, right, that introduction to the cross product. Today we're going to do some examples from the book, evaluating, computing that, and then kind of looking at that property and some actions of that cross product, right? So in section 12.4, the cross product, let me write this down and get started, with sharing my screen. Get it. Right, our multivariable calculus, we're looking at the cross product, okay? And so if we have two vectors, we'll do this with 3 dimensions. When we take the cross product, which should be a vector, so I should bring my little arrows in. So we have our two vectors. When we take that cross product of our two vectors, okay, this is evaluated by creating a matrix, a 3 by 3 matrix. Across the top row are unit direction vectors, I, J, and K, right? The X direction, Y direction, K direction for those unit axes. Okay. Then in order here, the first vector that we're using in our cross product, the middle row, what we're crossing it with, that secondary vector goes on the third row. And now we're going to expand this 3 by 3 determinant across the top row. So we're going to cross out that row, the column, boom. So we have these minors, right? This 2 by 2 matrix that's left over. That we're going to take the determinants. Let me actually write that down here rather than worrying about memorizing a formula. Again, I do this by utilizing that determinant. Always starts out with a subtraction next. Now, same idea. Now we're spanning across. We're doing the middle column, top row. So now we do so A1, B1, A3, B3 for the J. And then in addition, top row, last column, A1, B1, A2, B2. Okay. And then now doing that cross multiplication, subtraction, A2, B3 minus A3, B2, I minus A1, B3 minus A3, B1, J, right? So it's going to be that kind of I, J, K format. We bring down into our vector format later, that is then brackets, A1, B2 minus A2, B1 for the K component. Right? And so if you wish, keeping track of that negative, you can even put it in that then bracket form. And like I said, I don't necessarily memorize this formula, but more so the action of using that 3 by 3 determinant to find this resulting cross product. Okay, and so the result is going to be of that cross product, right? The result will be a new vector with the characteristic that it'll be orthogonal, right? Perpendicular, have a dot product equal to 0 to both vector A and vector B, right? Those two original vectors. This new vector is going to be orthogonal to. Now we can check that with our dot product work. back from section 12.3. So for example, borrowing this one from the book, push that up a little bit. So for example, let's go through it. One of these, this is on page 861 of the book. Let's check out here. Something interesting, but too terrible to work on. Let's do number 2, I guess. All right, so vector A, 4, 3, -2. Vector B, 2, -1, +1. Okay, and so just as an aside, vector A here, we can also see it as 4i plus 3j minus 2k. Vector B, just to get used to seeing these notations, 2i minus j, right? 1j plus 1k, or plus k there. Another way to represent these two vectors. All right. So with these two vectors given to us, let's find the cross product A cross B. Okay. So when I look at that, A cross B, 4, 3, -2, cross with 2, -1, 1. And again, with linear algebra, we might have seen some of this work before, or you will see it if you're taking linear algebra this semester. Okay. Going to compute that cross product, we're going to create this 3 by 3 determinant. Top row, our unit directional vectors, I, J, K. Middle row, that first vector, 4, 3, -2. Watch those signs, those positive negatives. Last row, the second vector, 2, -1, 1, right? I, J, K, keeping those aligned. So now as I start to compute, expanding across that top row, so that first column, first row. All right, so for our I remaining, that row, that column, copying that down, 3, -2, -1, +1. Then it's always a subtraction. Now for the J, that middle column, top row, we have 4, -2, 2, +1. And lastly, in addition, with the K, last column, last row, or top row, sorry, still, last column, top row, 4, 3 across the top, 2, -1. And so finishing up computing here, 3 times 1, 3, minus -1 times -2, +2. So there's my I, minus 4 minus -4. Watch the double subtraction, right? Plus -4 minus 6. Computing here, right? 1i minus 4 minus a -4, right? That turns into 4 plus 4. So that's minus 8. That subtraction's still there for the J. Plus -4 minus 6, a -10. We can make that a minus 10, right? Right, that's one format. Or probably more convenient, 1, -8, -10. All right, so with some graphing utilities, you might be able to graph that vector, set of vectors now, A, B, and now this result, this cross product, in the same coordinate system. Okay. But now let's check. Again, we can do both, but let's just do one of them. All right. Let's check to make sure if vector A is orthogonal to that result vector A cross B. Right. So again, if vector A was 4, 3, -2, our cross product we just computed and found 1, -8, -10. Watch those signs. So if we're orthogonal, right, remember that statement that our dot product is going to be equal to 0. Okay. That angle is going to be pi over 2 between these two, so the cosine would be 0. So if I look at that, 4, 3, -2, dotting it with 1, -8, -10, taking that dot product, what do we get? We get here 4 times 1 plus 3 times -8 plus -2 times -10, right? Multiplying component-wise, adding those results. 4 minus 24 plus 20, negative. And look at that, 4 minus 24, -20 plus 20, 0. Right? And we can do the similar actions taking the dot product between vector B and that cross product. And you should also get 0 there. Okay? So there's that quick calculation. Doing so. All right. So now let's try another example. Okay. There's that one. I'm going to slide this over. Let's look at another example, just kind of jumping our way through. Let's check out this problem, number 20. And this is on page 861 again. That's section 12.4. And this problem says, let's find 2 unit vectors orthogonal to both j minus k and I plus j. Okay. So some of these key phrases here, right? Orthogonal to both of these vectors. That means we're going to use a cross product, of course. All right, so whenever we need a vector orthogonal to 2 others, that cross product comes to mind. All right, so then j minus k, right? Thinking in 3 dimensions, that's 0, 1, 0. So there's my unit j vector, right? That y direction, minus 0, 0, 1, the k vector, the z. So doing that subtraction, 0 minus 0, 0, 1 minus 0, 1, 0 minus 1, -1, right? So there's that resulting vector. So that's like our vector A, right? I plus j, I, that x direction vector, adding, watch my operation here, 0, 1, 0, that j vector. Adding through, right? 1 plus 0, 0 plus 1, 0 plus 0. So that's like our vector B, if you will. And now we're going to do our cross product. Okay. So when I look at that cross product, taking 0, 1, negative 1, crossing 1, 1, 0, across the top, our unit direction vectors, I, j, and k. Now filling in our two vectors. And expanding, right? Dealing with our determinant of the 3 by 3 matrix. Jumping right into it, okay? So for our I, we're going to get here 1, negative 1, 1, 0, minus 0, negative 1, 1, 0, j, plus 0, 1, 1, 1 for the k. Again, double check my organization for that I, crossing out that top row, first column, 1, negative 1, 1, 0. Then for the j, right, the subtraction up front, middle row, or middle column, top row, 0, negative 1, 1, 0. Lastly, the k with a plus in front, top row, last column, 0, 1, 1, 1. Okay. Expanding across, now we get 1 times 0, 0, minus negative 1, minus 0, minus negative 1, j, plus 0, minus 1, k. Watch my signs. 0 minus negative 1 turns into positive 1. I, negative, negative makes a positive 1, but that minus out front stays subtraction, plus a negative 1, so minus 1. Okay. All right, or 1, negative 1, negative 1. So now this vector is going to be orthogonal to these two original vectors, right? Okay. So then, going back to our problem though, remember we wanted a unit vector. So to create that unit vector, we take our answer and we divide it by its magnitude, right? We'll talk about the pluralness of it in a second as well. So if I want a unit vector, I'm going to need to take my answer and divide by its magnitude. Okay. Taking those components squared, adding, and putting those underneath the square root. Right? So that's 1, negative 1, negative 1 all over the square 3, right? 1 squared, negative 1 squared, negative 1 squared, 1 plus 1 plus 1, 3. And so for that unit vector, 1 over the square root of 3, right? Dividing component-wise, negative 1 over root 3, negative 1 over root 3. Okay. So there's a unit vector. You can double check. It's going to be orthogonal to these two original vectors. And so now if we get back to kind of that introduction of vectors back in section 12.2, we talked about kind of the notation for vectors, right? This is kind of my direction in the X, my direction in Y, direction in Z, if you will, which direction we're pointing. And if we extend that vector instead of just being a unit vector, but we extend and stretch it out, right? We can be longer. But if we change that sign, we kind of, instead of like being pointed in one way, if you change the sign, it just flips the arrow over, right? It just makes it go backwards, if you will. It switches that direction. So what we can say is that, okay, well, that vector is going to be orthogonal. Let me kind of jump back, right? And so if you think back into some linear algebra, some possible work you would see with matrices before, right? A property of our cross product and really our kind of determinant of matrices is that when we take the cross product of two vectors, right, if we change the order of those two, okay, basically switching the rows in our determinant calculation, we get the same numerical value, but opposite in sign, right? So in this case, the sign changes, or in terms of vectors, the direction changes if we switch that order. But it's still going to be kind of along that same line. It's just where the point of our arrow on that vector is facing. But it's still going that same. So then when we start to think about these surfaces later, okay, all right, like think about a globe, okay, the Earth, for instance, that surface. Either we can have a vector pointing up out of the Earth towards the North Pole, right, towards the sun out of the Earth, right? That's one vector, right? Relatively, or even like my desk, for instance, right, is coming out of the desk, is coming out of the Earth, perpendicular there, orthogonal. Or we can flip it down, right? Go the opposite direction, down into the Earth towards the core, right? Down from your desk, down from the laptop, whatever it is, right? Still orthogonal, still a 90 degree, just going straight down. So it's orthogonal to the original surface, the original location, but just going the same. So whether we go change that direction up or down, right? This concept comes in. So we have this as our initial kind of just direct calculation, making a unit vector. That's one vector that's orthogonal to the original two, right? So for our problem then, the second or other unit vector orthogonal to the original vectors would be, so I'm going to slide this up. Okay, push this up, sorry for that. There's a lot of writing without it being present. All right, so for our problem then, we have our original, our first unit vector orthogonal to the original two. So that second, that other unit vector, that's going to be orthogonal to the two original vectors that we created that were discussed, would be, right, the negative of vector u, right? That is the negative of 1 over root 3, negative 1 over root 3, negative 1 over root 3, right? So changing those signs throughout, distributing negative 1 through, let me call it vector v. I can actually put a little hat over it, sorry, because the magnitude will be the same. But now this one's going to be negative 1 over root 3 for the I for the x, positive 1 over root 3 for the j for the y, positive 1 over root 3 for that k or that z component. And again, you can verify that that would still have magnitude 1, so it's going to be a unit vector, but it'll also be orthogonal to those two original vectors. Okay. Right on. Very good. So there's some of that work, also taking into account how we make a vector a unit vector. The big draw there, creating that vector that's going to be orthogonal to two original vectors by using that cross product, all that fun calculation work that we get nice solid solutions for. Okay. All right. So then a property that comes up, interesting. Okay. Recall we had with our dot product that the cosine of our angle theta was A dotted with B over the product of their magnitudes, right? And that A is orthogonal to B if and only if that dot product was equal to 0, right? That scalar result. All right, so we have that perpendicular aspect of it. Okay. So now, again, with some work with geometry, looking at these vectors, creating these different figures, right? Triangles within a coordinate system. Now we have that the sine of angle theta, the angle between those two, we can calculate by taking the magnitude, right? Because we're going to need a scalar of the cross product. The cross product itself is a vector. We need a constant, a scalar, so we need to take its magnitude. The magnitude of the cross product divided by the product of the magnitudes of each individual vector, right? Or again, theta in both of these is the angle between those two vectors. Okay. And so since we had that consequence that, well, if the cosine is equal to 0, that must mean your angle is pi over 2, right? 90 degrees, perpendicular or orthogonal. So now, in that same kind of context, that if the sine is equal to 0, that must mean that the angle is 0 or 180. Either those two vectors are going the same direction, right? The angle between 0, or they're kind of they're opposite, but they're pointing away from each other. The whole deal we just did with those two unit vectors, u and v, right? 180 or pi, they're going opposite direction, but they're still lying on that same direction, the same line. So in this case, we can say that vector A is parallel to B if and only if. Okay, I'll wait that notation in just a second because I think I forgot to mention. When we take that cross product, we're going to get a 0 vector, right? Each component zeroes out. It's not a scalar result, it's a vector result. And so before I forget, this is if and only if. that mathematical phrase. Right, so we talked about before looking for the kind of scalar multiples. Now we have this cross product to use to verify if two vectors are now parallel. Okay, and again, this somewhat goes back into some of the discussion, the properties of taking the determinant matrices, right? If our rows or even columns happen to be scalar multiples of one another, that determinant is going to be 0. Okay, if those expressions are linearly independent, those vectors, those rows, columns, then the determinant is going to be 0. Okay. All right. So we have that process now. We can use that to help either find the angle between two vectors using the cross product or verify if two vectors are parallel. Okay. And so then that said, the big part here is evaluating, finding those cross products to get that vector. And as we talk about, we use that nature, the fact that our created vector from that cross product is orthogonal to the two original, is going to be supportive for our work in graphing and managing some of these surfaces in vector format later on in this course. Okay. All right. So I'll leave it at that for now. Give you an opportunity to practice evaluating, finding the cross product and checking some of these other properties within section 12.4. Okay. All right. So I'll stop sharing here. This notes, these recordings will be online for us later for you to review and ask questions. Okay. So if you have any questions, please email me, let me know. I'll be putting up information about office hours as well. So that way, in case you do want to have a more kind of personal discussion with some problems you're facing, questions you may have, whatever it might be, we'll be able to meet via Zoom to discuss one-on-one if you desire. All right, so take care. Keep a lookout for Canvas. Any questions, of course, contact me. All right, so take care.